A very good morning to all of you. We will continue with our discussion on electromagnetic induction. Remember, in the last class we have discussed Faraday's laws of electromagnetic induction. We discussed that if you change the magnetic flux through a closed loop, then there is an induced EMF, and if there is a conductor in that loop, then that induced EMF generates a current. And we also introduced Lenz's law, which says that the induced current is so as to oppose any change in the magnetic flux. So, if you have a coil or a loop of conductor in which you increase the magnetic flux with time, then the induced current is so as to oppose this change. That means, it will produce a current in such a fashion that its magnetic field is opposing this change. So, it will be oppositely directed to the external magnetic field. Similarly, if you reduce the magnetic flux, then it will induce a current which will oppose this change. That means, oppose this reduction in magnetic flux and will add to the existing magnetic flux. And so, this is a very important law in electromagnetism and is, as I mentioned in the last lecture, has a large number of applications. We also actually I had shown right in the beginning of discussion of magnetostatics a very interesting experiment in which I showed that the induced EMF can generate eddy currents in bulk conductors, and those eddy currents can oppose the motion of these objects, and also I showed you that there is electromagnetic levitation. So, I had a solenoid with a aluminum block on top of the solenoid, and as I increased my current, the aluminum cylinder actually rose up, and that is a case of an eddy current. I want to discuss and I want to show you some more very interesting experiments on eddy currents, and this is the experiment. So, what I have got is two tubes of almost equal length. One is a PVC tube, this is the white one, and the other one is a copper tube, and here is a very strong magnet. This is not magnetic, this is not magnetic, both of them are non-magnetic, and what I am going to do is the following. I want to drop this magnet through these tubes. Now, if I drop a magnet outside, it is a mass which is being attracted by the gravitation, and so it falls with a certain acceleration. Of course, there is a viscous force, but that viscous force is very small in this small distance of propagation. Now, if I drop it in this plastic tube, except for the coverage by the plastic tube, it is going to fall at almost the acceleration due to gravity. And I want to see what happens when I drop this in either the plastic tube or the copper tube. So, let me show you this. Okay, so, I am going to drop the magnet in the plastic tube. As you can see here, it takes a finite time to come down. It is very small because the length is very small. Again, let me drop, it takes very little time. Now, I want to drop the same magnet in the copper tube. Here I am dropping it, and you see how much time it takes. It takes much longer to come out of the copper tube compared to the plastic tube. What is actually happening is, this is a magnet, a very strong magnet, and as the magnet enters the copper tube, copper is a good conductor of electricity. This moving magnet changes the magnetic flux across different cross sections of the copper tube, and because of Faraday's law, an induced EMF is generated in this copper tube. That induced EMF generates current because this is a conductor, and those currents oppose the motion of the magnet. So, effectively what is happening is, there is a force generated by the induced EMF which is opposing the motion of the magnet, and as the magnet is accelerating downwards, the induced EMF is generating a force upwards, the induced currents are generating a force upwards, which means it is like a viscous force, it is like dragging, it is not allowing the magnet to fall fast enough. And as you can see here, if I drop it at this instant of time, it takes considerable time to fall out compared to the plastic tube. So, let me drop once more in the plastic tube, there it is, and then there is a copper tube now. It is a considerable time, and that time difference is primarily because of induced currents generated here. This being a plastic tube, there is no current because this is not a good conductor. There is electric field generated. Please remember, as the flux changes, as the magnetic field changes, there is an electric field generated, but there is no current in this, but there is a current in this which is opposing the change and which is opposing the movement of the magnet through the tube. This is a very interesting example or a very nice demonstration of induced EMFs, and all of you can also do the same experiment, provided you get a strong magnet and a copper tube sufficiently thick so that it's conductive, it can conduct and create good currents. I want to show you another experiment with a longer copper tube, just to impress you the time it takes for the magnet to fall through a very long copper tube, and I will now just show you a much longer tube than this one, with a longer cross section, with a bigger cross section and a longer copper tube. So I want to show you that. So here is a copper tube, it's a long copper tube, it's about 1.5 meters long, and you can see this is the top of the tube here, and you can see at the bottom I have placed a piece of paper just to show you when the magnet falls. So this is a long copper tube, and it generates significant amount of eddy currents for the magnet to fall and resist the motion of the magnet itself through the copper tube. So this is a very interesting demonstration of generation of eddy currents, and I also want to show you another experiment using the same copper tube, where I will show you that the movement of a pendulum, which is actually a magnet, in front of the copper tube induces a lot of back resistance and slows down the motion of the pendulum. Now here is the same magnet now suspended from a string in the form of a pendulum, and if I give it an oscillation, you can see it oscillates with a certain frequency, and it has very little damping. It oscillates significantly fast, and because of air resistance there is some kind of a slowing down, but it is oscillating with almost same amplitude for a longer time. Now what I want to show you is I bring this copper tube below this magnet, and as you can see, immediately the magnet is slowed down because of eddy current generated in this copper tube. Let me show you again. I make the magnet oscillate, and if I bring the copper tube below the magnet actually generates eddy currents in the copper tube. Those eddy currents are such as to oppose the motion of the magnet, which is the pendulum, and so the pendulum stops. So if I do in this direction, for example, it also generates eddy currents, but the eddy currents are much lower and it takes a little longer to stop compared to this direction. It's very quickly damped out, and these demonstrations which I tried to show you today are demonstrations showing effects of eddy currents, and as I mentioned in the last lecture, eddy currents have a lot of applications in various branches of science and technology, and of course they also have problems because in transformer cores eddy currents are responsible for heating of the cores, and in that process the energy is lost from the system. So eddy currents have applications or also have problems in certain situations. So these were two very interesting demonstrations of eddy currents, and I want to continue with my lecture. Okay, so we just now saw some very interesting demonstrations of eddy currents generated by changing magnetic flux through a copper conductor, and these eddy currents are responsible for the experiment which I showed you, the slowing down of the magnet as it's dropped, as it accelerates towards the earth, and these are very interesting demonstrations of eddy currents, and they are also used in braking systems where eddy currents actually oppose the motion of the magnet, and they can be used for slowing down vehicles, for example. So let us continue with our discussion. In the last lecture I had also introduced the concept of mutual inductance. So if you have two coils, two arbitrary loops, for example, if this is carrying a current I1 and it produces a magnetic field, then this particular circuit will enclose a certain flux, magnetic flux generated by this current, and we had defined the flux of the second coil as M21 I1, and this is the mutual inductance. So, when two conducting loops lie close to each other, a current propagating in one of the loops induces flux through the second loop, and that flux is proportional to the current passing through the first loop, and that proportionality constant is called the mutual inductance. In fact, I also showed you that M21 is equal to M12. So, if I pass a current through the upper coil, the amount of flux that is passing through the lower coil is also proportional to the current passing to the upper coil, and the proportionality constant happens to be the same. And I had used this property in discussing one very interesting example, where it is much easier to calculate one of the mutual inductances as compared to the other. After this, I also introduced the concept of self-inductance. So, if you have a coil like a solenoid, passing a current through the solenoid creates a magnetic field. So, each loop of the solenoid is also enclosing the magnetic flux generated by the solenoid. So, there is a flux passing through each loop of the solenoid. So, through the entire solenoid now encloses a flux generated by the current passing through the same solenoid, and that flux is referred to, that gives me a self inductance. So, if I had like last time, if I had a solenoid here, and if I pass a current through the solenoid, then the flux through the solenoid is equal to sum L into I, and this L is called self inductance. And so, self inductance is a flux enclosed by a circuit because of a current passing through the same circuit. Mutual inductance is between two different circuits or two different loops of current, and this flux is very important because whenever the current changes, the flux enclosed by the loop will change. For example, if I change the current in the solenoid, the flux enclosed by the solenoid will change. A changing flux induces an EMF, and that EMF will oppose the change in current. So, when you look at self inductance, it induces what is called as back EMF. So, if you try to change the current in the solenoid, then the changing current induces the changing magnetic flux. A changing magnetic flux induces an EMF, and according to Lenz's law, that induced EMF or a current is so as to oppose the change in the current. So, when you try to increase the current, there is an opposing force which is forcing you to slow down. So, this is called the back EMF, and we had seen some examples in the last class. Also remember, the unit for inductance is Henry. 1 Henry is equal to 1 Tesla meter square by ampere. It is an SI unit, and I want to discuss one more example of a toroid. So, we are looking at a toroid. Remember, in one of the earlier classes we had discussed the magnetic field of a toroid. So, toroid consists of a structure like this with loops like this, for example, surrounding the entire toroid, closely bound loops. So, current comes in from here and goes out from here. So, let me assume that this radius is small r and the current passing through is I. So, mean radius is equal to small r, and area of cross section that is this area is A. That is area of cross section, not the cross section of the entire toroid, but the cross section of the cross section of the toroid here. So, now to calculate the inductance, I must know the flux. So, to calculate the flux, I must know the magnetic field. So, if the area of cross section, if the dimension of the toroid is small compared to the average diameter, I can assume that the magnetic field is uniform uniform within the toroid, and by symmetry, as we had discussed before, the magnetic field must be in this direction. So, the magnetic field I can calculate by using Ampere's law. So, I take a loop like this. So, the Ampere's law is B dot dl is equal to mu 0 times I enclosed. B is the same all across the circumference of the circle, and it is pointed along the dl vector. So, dl vector at every point is like this, here is like this. So, B and dl are parallel. So, B dot dl is B times dl, and B is the same all across the circumference of the solenoid of the toroid. So, I can take B out, and integral dl becomes simply 2 pi r. So, 2 pi r into B is equal to mu naught times. Now, what is I enclosed? Remember, if there are total number of turns is nt, there are nt turns in this toroid, then the total current enclosed is nt times I. So, each of these loop encloses a current I. There are nt such loops, total number of loops. So, the total current enclosed is nt times I. So, magnetic field is equal to mu naught nt by 2 pi r into I. So, I am going to assume this magnetic field is uniform across the cross section of the toroid, and once having calculated the magnetic field, I can calculate the magnetic flux. Through each turn. Is equal to the magnetic field into area, which is equal to mu naught nt by 2 pi r into A into I. So, this area is the area of each loop of the toroid. The magnetic field is B. So, the total magnetic flux linking all the nt turns of the toroid are obtained by multiplying this by nt. So, you will get mu naught nt square A by 2 pi r into I. So, the total magnetic flux is given by mu naught nt square A by 2 pi r, because this is the flux enclosed by each loop of the toroid, and there are nt loops in the toroid. So, each of the loops of the toroid encloses a flux, magnetic field into area, and there are nt number of loops. So, the total flux enclosed is this, and this gives me a self inductance as, because this I will write as L times I, and so self inductance L is equal to mu naught nt square A by 2 pi r. So, that is the self inductance of a toroid. I can put some numbers and calculate. So, let me put in some numbers. So, let me write here self inductance of the toroid is mu naught nt square A by 2 pi r. So, as an example, let me take the total number of turns as 200, an area of 5 centimeter square, which is 5 into 10 to the minus 4 meter square, an average radius of 10 centimeters, which is 0.1 meters, and so the inductance is 4 pi 10 to the minus 7 into 4 times 10 to the power 4 nt square into area is 5 10 to the minus 4 divided by 2 pi times r, which is 0.1, and if you substitute all this, you will get 40 times 10 to the minus 6 Henry, which is equal to 40 microhenry. 10 raised to minus 6 is a micro. So, the self inductance is 40 microhenry of this toroid. Now, if I take this toroid and change the current in the toroid, so if I change I through the toroid, and if di by dt, if the rate of change of current is equal to 5 amperes in 10 microseconds, which is 5 into 10 to the minus 10 to the power 5 amperes per second, that is the rate at which I am changing the current, the induced EMF minus L di by dt, which is equal to minus 40 microhenry into 5 into 10 to the power 5, which is equal to minus 20 volts. So, you will generate an induced EMF of 20 volts across the toroid if you change the current at the rate of 5 amperes in 10 microseconds, and that gives you induced EMF, and depending on the resistance of the toroid, this induced EMF will generate a current to the toroid, and that will be the one can calculate the kind of current that is generated in the toroid once I know the resistance of the coil of the toroid. Okay, so all this discussion has given me the concept of self inductance and mutual inductance. Now, remember in electrostatics, when we were discussing electrostatics, we discussed also the energy that is present in electrostatic fields. So, I want to use the similar argument to calculate, to show you that in magnetic fields there is energy stored. Energy is stored in the form of magnetic fields, and to show this, let me take the example of a solenoid. So, let me calculate the energy in magnetic fields. So, I want to calculate what is the energy stored in magnetic fields. So, for this let me consider a solenoid, a coil with self inductance L. So, I consider a coil, for example solenoid with self inductance L. When the current in the coil changes with time, for current changing with time, I will get an induced EMF. Minus L di by dt. L times I is the flux, L is the self inductance, L times I is the flux. So, minus L di by dt, which is minus d phi by dt, is nothing but the induced EMF. And so, this induced EMF, as I have been discussing, the minus sign includes is the fact that it is trying to oppose any changes in the magnetic flux. For example, here the current, when you try to increase the current, there is an opposition to the increase in current. When you try to decrease the current, there is an opposition to decrease in current. And so, whenever I try to increase the current, there is an opposition to my increasing the current, which means I must do extra work to increase the current against the opposing forces. And so, when I am increasing the current, I am doing work on the system to increase the current, and that work which I am doing actually finally gets stored in the form of a magnetic field within the solenoid. To show this, so what is EMF? EMF is nothing but the work done in carrying a unit charge across the complete circle, across the complete circuit. So, E is equal to work done in carrying, in moving a unit charge through the circuit. So, because it is a back EMF through the circuit. Because it is a back EMF, I must move it against this EMF, and so the work I must do is given by minus E, work done by the external agent I must work against this induced EMF, and so I must do a work of moving a unit charge which is minus E. Now, what is current? Current is nothing but the amount of charge moving per unit time. If I have a current I, the amount of charge that I am moving across the circuit per unit time is nothing but current. So, I represents current I represents total charge crossing the circuit per unit time. So, if I neglect resistance or resistive heating, the work done per unit time will be equal to, I call this dW by dt. The work done per unit time is minus E times I. Please note, work done in moving 1 unit charge through the circuit is minus E. I represents the amount of charge flowing crossing per unit time. So, I must move I charges per unit time through the circuit, and for moving each charge I am doing a work minus E. So, the amount of work that I am doing per unit time against the induced EMF is essentially minus E times I, which is nothing but minus I minus L I d I by dt. E is, so this is plus. So, E is minus L d I by dt, with a minus sign here it becomes L I d I by dt. So, I can calculate the total work done in increasing the current from 0 to I will be equal to W is equal to L integral I d I 0 to I, which is equal to half L I square. So, this is the work done per unit time, and if I have to increase the current from 0 to I, the work that I need to do is integral of this, and that becomes simply W is equal to L times dt cancels off, and I get I d I, and that is half L I square. So, this is the work that I need to do to increase the current from 0 to I, and this work that I am doing is actually stored in the form of magnetic field inside the inductor. So, this particular solenoid or the circuit, actually if I have increased the current from 0 to I have done some work, and that work is stored in the form of a current passing through the solenoid or the coil or the magnetic field. So, I want to interpret this in terms of magnetic fields. So, this is in general, this is for not just for solenoid, for any inductance, any circuit containing a self inductance L, there is a current stored in the self inductance, and that is simply half L I square. So, I want to take an example here, and that example I want to take a solenoid. A closely bound solenoid. So, closely bound and very long. So, I will assume that the magnetic field is uniform. Within the solenoid. And is 0 outside. As we have seen before, in a solenoid, closely bound solenoid, the magnetic flux, the magnetic field is within the solenoid is uniform, and what is the magnetic field? We have already calculated, B is equal to mu naught N I, where N is the number of turns per unit length, and the current passing through is I. Now, in the earlier lecture I had actually calculated the inductance of the solenoid, and the inductance came out to be, self inductance came out to be L is equal to mu naught N square pi R square into L. Self inductance of a length L of the solenoid we had calculated is mu naught N square pi R square into L. So, what is the energy stored? Energy stored in the solenoid half L I square, which is equal to half mu naught n square pi r square into L into I square. Here r is the radius of the solenoid. So, I can write this as half mu naught n square I square into pi r square into L. Now, let me write this in a slightly different form. So, I write this as 1 by 2 mu naught n I whole square pi r square L. So, I multiply and divide by mu naught, and I write this as 1 by 2 mu naught n I whole square into pi r square into L. Now, what is mu naught n I? I just now saw mu naught n I is nothing but the magnetic field within the solenoid. And what is pi r square L? Pi r square is the area of the solenoid multiplied by the length of the solenoid is the volume of the solenoid. So, this is the volume. So, this is the volume of the solenoid, and this is the magnetic field. So, I can say that this solenoid has so much energy stored in the magnetic field. This is the magnetic field. So, let me write this as 1 by 2 mu naught B square into volume. This is B of the solenoid, and this is the volume of the solenoid. So, I can write this energy stored, which I have calculated as half L I square, has 1 by 2 mu naught B square into volume. So, what does this give me? It gives me that this must be the energy density of the magnetic field. So, I get an expression for the energy density, which is the energy per unit area per unit volume U B is equal to half 1 by 2 mu naught B square. That is a very important expression. So, what I have seen is I can interpret the energy that I have spent, or the work which I have done in charging up the circuit or a solenoid in this example to increase the current from 0 to I was half L I square, and I wrote that half L I square in a slightly different form, in a form which looks like this, is 1 by 2 mu naught B square. B is the magnetic field within the solenoid into volume of the solenoid. So, I can interpret that the energy that is being stored in the solenoid is in the form of a magnetic field, and that magnetic field has a energy density, which is energy per unit volume of 1 by 2 mu naught B square. And so, this is a very important relationship. Now, although I have derived this for a solenoid, this is a very general relationship that if you have a magnetic field B at any point, it creates an energy density of B square by 2 mu naught, and this is very similar to what we had done for electrostatics. Electrostatic energy stored per unit volume U E was 1 by 2 epsilon 0 E square. That is the energy density of electrostatic fields, that is the energy density of the magnetic field, and they are similar relationship. Epsilon 0 gets replaced by 1 by mu 0 here. So, electric fields and magnetic fields store energy, and I had obtained this by taking an example of a capacitance, parallel plate capacitor, and here I have done this using an example of a solenoid. But please remember, these expressions are very general, they are not restricted to parallel plate capacitor or a solenoid, and although I have not obtained this very generally, these equations are valid in general. So, whenever you have an electric field and a magnetic field, they will store, you can store energy in the form of fields, the electric and magnetic fields. So, let me look at an example. So, suppose I have a magnetic field B of 1 Tesla, then the energy density, which is equal to 1 by 2 mu naught b square, which is equal to 1 by 2 times 4 pi 10 to the minus 7 into 1, which is equal to 1 by 8 pi 10 to the power 7 joules per meter cube. So, that is the energy stored in this magnetic field. If you have 1 Tesla magnetic field at a certain point, there is a magnetic field energy density of 1 by 8 pi 10 to the power 7 joules per meter cube in that volume. So, if I look at a solenoid, for example, if I take a solenoid of n is equal to 1000 turns per meter, and if I pass a current I is equal to 1 ampere through the solenoid, the magnetic field is mu naught N I 4 pi 10 to the minus 7 into 1000 into 1, which is equal to 4 pi 10 to the minus 3 minus 4 Tesla, and the energy density U B 1 by 2 mu naught B square. So, I can again write this as 1 by 2 mu naught into mu naught square n square I square, which is equal to mu naught n square I square by 2, and I can substitute this as 4 pi 10 to the minus 7 into 10 to the power 6 into 1 divided by 2, and that is equal to 2 pi into 10 to the minus 1 joules per meter cube. 0.2 pi joules per meter cube is the energy density of the solenoid. You can interpret is the passing current which is storing the energy, or the magnetic field which is generated within the solenoid which is storing the energy. So, that gives you an idea of the kind of energies that we can store in magnetic fields in this solenoid. Now, all this time we have calculated situations where the magnetic field was uniform. So, I had taken a toroid where the magnetic field was almost assumed to be uniform, then I took a solenoid where the magnetic field was uniform. Now, I want to take an example where the magnetic field may not be uniform. So, this is a non-uniform magnetic field. So, I want to take the following example. So, I have two coaxial conductors. There is a current I passing through the inner conductor in this direction and it is returning from the other conductor. So, this radius is A and this radius is B. So, let me draw the two cross sections, they look like this. This is A, this is B. So, current is flowing in this direction in the inner solenoid and coming back in the outer solenoid, sorry, in the conductor. So, the inner conductor carrying current in the forward direction here, and the same current is reversing in the outer conductor. So, I here and I here. So, I want to calculate what is the self inductance of this per unit length. So, this is a long cable, for example. So, I want to calculate what is the self inductance. Now, I can calculate self inductance either by calculating the flux enclosed by this system, or I can calculate the energy stored in the system and equate it to half Li square. So, first let me calculate the energy stored. So, for all this I need to calculate the magnetic field in the system. Now, this is a surface current propagating through the outer surface of this inner conductor and the inner surface of the outer conductor here. First thing you can notice is because of symmetry, magnetic field will not be dependent on the position along the length of the conductors. Magnetic field cannot have a radial component. Magnetic field has to be azimuthal. It has to be azimuthal, just like in earlier examples. When you take a long, infinitely long conductor, it creates a magnetic field which is azimuthal, which is circulating around the conductor carrying current. So, I know that the magnetic field will be azimuthal, that means in this direction, this circular direction like this. Now, because of the current I passing in the forward direction and the same current I in the reverse direction, I leave it to you to show that there is no magnetic field within this area here and there is no magnetic field outside this area. So, the entire magnetic field is in this volume here. This is the area in which the magnetic field will be existing. So, to calculate the magnetic field, what do? I take, these are the two conductors, and I take a circular path of radius r. So, integral B naught d l is equal to mu naught I enclosed. So, because the magnetic field is like this and I am integrating like this, I will get 2 pi r into B is equal to mu naught I. So, B is equal to mu naught I by 2 pi r. So, that is the magnetic field, and that magnetic field only exists between A less than r less than B. And for r less than A, magnetic field is 0, for r greater than B, magnetic field is 0. So, I leave it as a problem to you. Please show that there is no magnetic field for distances less than A, and there is no magnetic field for positions outside this coaxial pair of conductors. So, that is the magnetic field generated. So, now I can calculate the energy density of the magnetic field. U b is equal to 1 by 2 mu 0 b square, which is equal to 1 by 2 mu 0 I by 2 pi r whole square, which is equal to mu 0 I square by 8 pi square r square. Mu 0 I square 8 pi square r square, that is the energy density stored in the magnetic field. Now, please note here that the magnetic field is not uniform, the energy density is not uniform. The energy density is maximum close to the inner conductor where r is small, where r is close to A, and as r increases, as you move away towards the outer conductor, r increases, the magnetic energy density decreases, because magnetic field itself is decreasing. So, here is an example where the magnetic flux magnetic energy density is not uniform across a cross section, it varies with position. Now, to calculate the total energy, I must integrate. So, let me calculate the energy in a length L. Let me put a small l in a length small l. So, I must take a volume. So, what I need to do is the following, that I take, so let me draw a figure here. So, I have this inner conductor and an outer conductor. So, I take a radius r and r plus dr. This thickness is dr and of length L. So, this is the coaxial cables are going like this, and I want to take a length L. So, what is the integration I need to do? So, there is no variation of magnetic field along the length. So, I take a cross sectional area between r and r plus dr and this volume, and I calculate the energy, and I integrate from r is equal to 0 to A to B, that is from the inner conductor radius to the outer conductor radius. So, what is the volume, elementary volume? So, this area of this multiplied by the length. So, area of this is circumference of this multiplied by the thickness 2 pi r dr, that is the area, multiplied by the length of the cylinder gives me the volume of this thin cylinder here. So, 2 pi, so r is the radius of the inner circle, dr is the thickness of this. So, 2 pi r dr is the area of this, multiplied by the length is the volume. So, that elementary volume is equal to 2 pi r dr into L. So, the total energy, total magnetic energy is equal to integral u b into 2 pi r dr into L, and r goes from A to B, because the magnetic field is finite only from A to B. So, this is nothing but if I substitute mu naught I square by 8 pi square into 2 pi into r dr by r square A to B into L. So, I have substituted this magnetic field density mu naught I square 8 pi square, r square is inside the integral, and 2 pi comes out of the integral, L comes out of the integral. So, this is equal to nothing but mu naught I square by 4 pi L integral A to B dr by r. Now, dr by r is nothing but log r, and if I integrate from A to B with limits, I will get the total magnetic energy is equal to mu naught L by 4 pi into log P by A into L into I square. So, please note this integral is log B by A. So, the magnetic energy stored in a length L of this coaxial conductor is this quantity multiplied by I square, and I will write this as half L I square, because I know that the magnetic energy is half L I square. So, I get the self inductance L as mu naught L by 2 pi log P by A. So, that is the self inductance of a length L of this coaxial conductor of inner radius A and outer radius of the conductor as B, and the magnetic field that is contained within this pair of conductors stores energy, and that energy is half L I square, and where L is the self inductance of this length L of this coaxial pair of conductors. So, I can define a self inductance per unit length as mu naught by 2 pi log P by A. So, let me consider an example. So, let me take a coaxial cable of A is equal to 5 millimeters, B is equal to 8 millimeters. So, L is equal to 4 pi 10 to the minus 7 by 2 pi into log of 8 by 5, and if you do calculation, this will give me 9.4 10 to the minus 8 Henry per meter. So, you can calculate this log factor here, and you will get an inductance per unit length of 9.4 10 to the minus 8 Henry per meter of this cable. So, this gives you an idea of calculating the self inductance, and what I have done here is actually calculated the self inductance by calculating the energy stored. I took this problem of a pair of coaxial conductors. I calculated the magnetic field. The magnetic field is non-uniform between the two conductors. Then I calculated the energy density of the magnetic field, and I found that the magnetic energy density is non-uniform. It goes as 1 by r square. There is more energy stored closer to the inner conductor than the outer conductor, because the magnetic field is decreasing as you move away from the inner to the outer conductor. And then, so when I calculated the total magnetic energy, I must do an integration. I cannot multiply the energy density by area. So, I do an integration, and that integration I carried out, and I carried out by calculating the elementary volume and then calculating the total energy density, and that came out to be of the form half L I square, and I got a expression for the self inductance of this coaxial cable. So, that is also one of the ways of calculating self inductance. I calculate the energy stored, and from there I can estimate the self inductance. In fact, for this problem I can also calculate the self inductance by calculating the flux. So, for example, if this is my these are my two conductors, now magnetic field is going in the azimuthal direction. So, magnetic field is if the current is going like this, magnetic field is going like this, it's circulating around the conductor. So, to calculate the flux, what I must do is to take a surface perpendicular to this. So, I take a surface like this of length L, and I can calculate the flux through this, and I leave this as an exercise to you. You can calculate the flux, it is the magnetic flux phi b is equal to B dot d A, which will come out to be mu naught I by 2 pi L into log B by A, and this can be written as L times I, and I get an expression for L which is mu naught by 2 pi log B by A, mu naught L by 2 pi into log B by A, which is exactly the same as what we had obtained from energy density calculation. So, both these calculations give me the same. In this problem, it was possible to do both types of calculations, and I got the same result. So, we will stop the discussion here, where let me recall, today we saw some demonstrations of eddy currents, and then I discussed some examples of flux storage and self inductance, and I showed you that when you have a magnetic field, you have energy density, and that energy density of the magnetic field is half mu naught 1 by 2 mu naught b square, and using this we can actually calculate we can assume or we can consider the energies to be stored in the form of magnetic field inside circuits. So, I will stop here, and in the next class we will briefly discuss how to use this induced flux to generate currents, AC and DC currents, and we will continue with the discussion on electromagnetic induction. Thank you very much.